I promise electricity is not scary as it looks at first. It's mostly just a few key ideas and a handful of formulae that you need to use over and over again. Let's break it down nice and easy. An electric current is defined as the rate of flow of charge. So remember, rate means you divide by time. The formula for electric current is I is equal to Q over T. Charge is measured in coulombs, time is measured in seconds, current is measured in amps. Now let's think about a simple power supply like a cell or a battery. Now, on the negative terminal, you have large number of electrons, so it has a high electron pressure. On the other side, there are less electrons, it's electron deficient. So the electrons in the metallic conductor here are attracted towards the positive side and is repelled away from the negative side. So obviously the direction of the flow of electrons is this. So remember, the flow of electrons is always from negative to positive. Now the direction of what we call the conventional current, however, is the opposite. And here's the next basic formula you need to know: potential difference or voltage. So by definition, potential difference is the work done per unit charge. So it's work done divided by charge. V is equal to W over Q. The units are joules for work done, coulombs for charge, and volts for voltage. So 1 volt is the same as 1 joule per coulomb. Here you can see the symbols you need to know for GCSE electricity. Pause the video and take a minute to quickly think about each one and whether you know the names of them. When you're ready to check the answers, press play. Here are the answers. Open switch, closed switch, obvious. Cell is here. And this one here is a battery. So the difference is a battery consists of 2 or more cells connected together. Diode, resistor, variable resistor. It's easy to memorize it. It's easy to memorize this because a variable resistor has this control, so which means the resistance can be changed. Lamp, fuse, just like a resistor, but the line goes all the way through. Ammeter A, voltmeter V, motor M. They're very obvious. Thermistor, this one. This is a popular exam question. I've seen this in the past as 1 mark question. They just ask you to draw the symbol of the thermistor, the 1 mark. LDR, again, stands for light dependent resistor, and you can see light coming in. So it's a resistor here and a light coming in, obviously light dependent resistor. And the next one, LED, here you can see the diode, and here's the same diode, but what's this? This is light going out, light is being emitted, so light emitting diode, LED. Resistance is the property of a material that opposes the flow of current through it. Mathematically, resistance is defined as voltage divided by current. R is equal to V over I, or you can even rearrange this to the form V is equal to IR. You get a lot of exam questions from this formula. Let's have a look at a simple question here. A resistor has a resistance of 10 ohms, that's R, and a current of 2 amps, I. What is the PD across it? So V is equal to IR, and the answer is 20 volts. Ohm's law. The current through a component is directly proportional to the PD across it, meaning if you double the potential difference, the current will double. If you triple it, it will triple. If you half it, the current will also half. The current through a component is directly proportional to the PD across its ends if temperature and other physical quantities remain constant. So V is directly proportional to I. V is equal to some constant times I. Resistors are divided into 2 main categories as ohmic and non-ohmic. So ohmic resistors obey Ohm's law. So the current voltage graph is a straight line through the origin like this. Example, a metallic conductor at constant temperature. Now this is really important because if the temperature changes, resistance can change. Now in practice, many resistors do not obey Ohm's law. Those are referred to as non-ohmic resistors. Examples of non-ohmic resistors are the filament lamp or a diode. In a filament lamp, the current increases with potential difference, but then what happens is it kind of comes to a plateau around here because as the temperature increases, the resistance increases. And a diode is a slightly peculiar one compared to the others because this graph is asymmetrical. Investigating IV graphs. To do this experiment, you need this experimental setup. There's a power supply, and this is the component that is being checked. In this example, it's a resistor, voltmeter connected in parallel, ammeter connected in series, and a variable resistor here to change the resistance as we go. So what we need to do is change the value of R, and you can record the PD and current. Same thing again and again and again. In physics, you need to take a minimum of 6 pairs of readings to produce a valid graph. Then you can plot the current voltage graph. To get the negative side of the graph, all you need to do is reverse the polarity of the power supply, then you can get those things. Now, you can change the resistor with a filament bulb, and then you can produce a graph for that. Then you can change this to a diode. Investigating resistance in a wire. For this experiment, we need to take a resistance wire, and you need to mount it on a meter rule, like this one here. Then you need to use a crocodile clip to connect this one, an ammeter to measure the current, and a voltmeter to measure the voltage. And then here's the power supply. And this one here is what we call a sliding contact. Now, first, you can connect the sliding contact to the 100 centimeter mark. So you can use the full length of the wire, like this. Then you record the length, record the PD and current. Now, resistance is equal to V over I, so I can divide the voltage by the current, so I can work out the resistance at that point. Then you move this to 90 centimeters. And then you get your, record the length, PD, current, and then you can calculate the resistance. And you repeat it like that all the way up to 10 centimeters. Then you can plot a graph of resistance against length. So here you will get a straight line graph to the origin with a positive gradient. The difference between series and parallel circuits is a really important thing in GCSE physics. Now, in a series circuit, components are placed one after the other, and there is only one path for the current to flow. And the current through each component is the same. Now, let's see. If the current starts from here, only one path. Here it's 2 amps, 2 amps, through this one, through this, and everywhere the current is the same. It's 2 amps. But in a parallel circuit, components are placed side by side. So this one and this one and this one side by side. And there are multiple paths due to junction. So the current can come like that. And the current can split up. So you get 2 amps here, 3 amps here. That can again split up depending on the resistance. 1 amp here, 2 amp here, like that. So the current splits up. Now in a series circuit, voltage splits up. Now you can see there is 10 volts and it splits up as 3, 5 and 2. In a parallel circuit, however, voltage does not split up. And you see there's a 6 volt power supply, and here's 6, here's also 6, the other one also feels the full 6. If a fault develops in one component in a series circuit, all others will not work. Now imagine if this one broke for some reason, there's no path for the current to go now. The current cannot really go because there's a gap, so everything else will stop working. However, in a parallel circuit, if a fault develops in one component, others will still work. Now let's say here, this one got damaged for some reason. Now, current cannot go through that branch, but here the current can still go through the other branches, like this one and the other one, so others will still work. In a series circuit, all components are controlled by one switch together. Now let's say if you put a switch here in the circuit, it will control the circuit altogether. However, in a parallel circuit, each individual component can be controlled by separate switches. Now let's say you put a switch here. That will only control this. If you put a switch here, that will only control this resistor here. So example of series circuits is using Christmas lights or fairy lights. Here is a typical GCSE exam style question on series circuits. If you want to give this a try, pause the video and give it a try. When you're ready for the answer, press play. Step 1 is to find the total resistance. So how do you find the total resistance? There's 4 ohms here, 6 ohms here. So the total resistance is 6 add 4, 10 ohms. Step 2 is using V is equal to IR for the whole circuit. So let's do that. TD or voltage provided is 20, I don't know, R is now 10. So if you divide both sides by 10, I is equal to 2 amps. So I know the reading on each ammeter is 2 amps. So in the last step, to find each voltmeter readings, you are going to use V is equal to IR for each resistor. Let's do it for this one. V1 is I is 2, R here is 4, 2 times 4, 8 volts. V2, right, for this one, I is 2 times 6, and the answer is 12 volts. And you can see beautifully, this 8 and this 12 add up to 20. Now here you can see a typical GCSE exam style parallel circuit question. Again, pause the video and give it a try. When you're ready for the answer, you can press play. Now remember, in a parallel circuit, the voltage across each branch is the same. So this is 8 volts. So obviously, voltmeter 1 is 8 volts. Voltmeter 2 reading is also 8 volts. Now, how do I find the current in each branch? So I just found the current in each. So I'm now going to find the current in each branch. So all I need to do is step 1, write V is equal to IR. Now let's write it for this one here. So V is equal to IR. Now I can see the current in the branch here is 0.4 amps. Now let's do the same thing to the other one. For this one, V is equal to IR. Divide both sides by 10, and you can see the current here is 0.8 amps. So the reading on A3 is 0.8 amps. Now look at this. We have 0.4 amps going down this branch, and we have 0.8 amps going through this branch. But where did those two currents come through? Those currents can only come through the branch above. So obviously, the current in this branch should be the sum of these two, which is 1.2 amps. So that would be the reading of ammeter A1. Now, I have this easy way of explaining this, and I have found over the years that students find this really helpful to understand it. So think about a marathon or something, right? But normally they are supposed to go in the same way. But let's say 3 people run along this route and 4 people run along this route. Now, obviously, if there's only one route to come to that junction, the total number of people who ran here must be obviously 7. So just like that, 0.4 and 0.8 is 1.2. LDRs and thermistors. Light dependent resistors. As the name implies, the intensity of light decides the resistance. In bright light, the resistance is low. In darkness, the resistance is high. Now, to memorize it, to understand it, let's use this example. Imagine there's a room and there's no other light supply except for this one bulb. Now, it's a completely dark room, and you have a light dependent resistor on one side, and if you keep the light bulb on the other side, so the intensity of light is low because obviously it's far away, and the resistance could be, let's say, 10 ohms, just made up. Now, if you bring it really close to it so that the intensity of light is high now, the resistance could now go down to 2 ohms. So the idea is bright light, low resistance. So bright light, 2 ohms. Darkness or low intensity of light, high resistance, 10 ohms. Thermistors, as the name implies, therm, heat, changes the resistance depending on the temperature. Just like an LDR, when the temperature is high, when the hot conditions, it has a low resistance. In cold conditions, the resistance is high. Now, let's think about a practical example to understand it like before. Say, if a thermistor is kept in cold water, now let's say this is only at 10 degrees Celsius, the resistance could be 100 ohms. Now, if you increase the temperature of water to, let's say, 70 degrees Celsius, let's assume that the resistance goes down to 5 ohms. So what that means is hot conditions, low resistance. Look, hot conditions, low resistance. Cold conditions, high resistance. Sensing circuits are used to respond to changes in the environment. Now, how do they work? In bright light, the LDR has a lower resistance. Now let's say, for an example, the resistance of the fixed resistor is 50, and let's say in bright light, the low resistance of the LDR is 2. Now, look at the ratio. It's only 50:2. So a very small proportion of the input voltage, 10, will be across the LDR. Now, in this example, I did the calculation. The voltage across this LDR is about 0.4 volts. That's a very small value. Will the light bulb illuminate? No, it will not, because it's such a small PD. Now, let's say what happens in darkness. When it is dark at night, the LDR resistance increases. Now, let's say it's not 2 ohms anymore. When it's dark, it's 150 ohms. Now, the fixed resistor, that is fixed, that is still 50. Now you can see 3/4 of the input voltage, which is 7.5 volts, is across this one. Now, that is a high voltage, high PD. So what will happen? The bulb illuminates. This is a sensing circuit using a thermistor. In hot conditions, the thermistor has a lower resistance. Now let's say the fixed resistor has a resistance of 100 ohms in both cases. The lower resistance is 2 ohms when it is hot. Now, the input voltage is 10. Now, a very small proportion, like 0.2 volts, is across the thermistor, which means most of it, 98% of it, 9.8 volts, is now across the motor. So here's a motor, so which is basically, you know how the fan works, right? So this is connected to a fan. Motor is the fan, so the fan will work when it is hot. So that's good. Now, what happens when it is cold? When it is cold, the thermistor resistance is high. Now let's say the thermistor resistance now becomes 300 ohms. Now you can see the ratio is 1 to 3. So most of this input voltage, 7.5 volts, is now across the 300 ohm. So what will happen? The fixed resistor has a smaller potential difference, which is only 2.5 volts. So the fan will not work. So either it will not work, or sometimes you can have an arrangement where the fan will work, but at a much slower speed. Direct current and alternating current, DC and AC. Now in DC, the current starts from one direction and it goes like that, and it just goes like that. So there is a constant current and the current flows in only in one direction. Example, current provided by a normal battery or a cell. But in an alternating current, the situation is a little different. Now, this is an AC supply and it changes the polarity. If it's plus and minus now, the next moment it becomes minus here and plus here, like that. So the idea is this pushes the current first in one direction and the next moment in the other direction, and so on and so forth. So what happens is the current has a positive component. It goes in one direction and then it switches the direction, and then the other direction again, and then the negative direction. So current first flows in one direction and then in the opposite direction. Now, here you need to know that UK mains electricity is AC, that voltage is 230 volts, and the frequency means the number of times that it changes direction per second is 50. So we call it, the frequency is 50 hertz. Here's a question for you. Pause the video and think for a moment which of these are AC and which of these are DC. Now, here's the answer. Obviously, one is DC because it's in one direction, and the third one is AC because it goes like that, like this. Now, it's the second one and the fourth one that most people make mistakes on. They think this, sometimes people think this is AC because of the shape of it. However, remember, it has to go to the negative side, positive side here. So this one is AC, all others are actually DC. Yes, there is a variation of current. Here there is a variation of current, but they are also DC. Why? Because there is no current in the negative region. Wiring a plug. You need to know about different wires in a plug. So this brown one is the live wire, and this blue one is the neutral wire, and the green and yellow striped one is the earth wire. Now the live wire brings the current into the appliance. Neutral wire just completes the circuit and takes the current out. The earth wire is basically a safety feature. The fuse here is a glass cartridge with a thin wire inside, which is again a safety feature. So basically what happens is if the current gets too high, it will melt. Then you can see here there's a cable grip to secure the cable, and the outer insulation provides extra plastic covering to make sure that the users are not touching any metal parts. Earthing and fuses. Let's think about a washing machine. Now let's say the working current of a washing machine is 4.5 amps. So a 4.5 amp current will go through the motor, and then it will do its job, and the neutral wire brings this back out, 4.5 amps. Now here we have a fuse. So the job of a fuse is to melt if the current goes above a certain value. So here's a diagram of a fuse. And the value here, 3 amps, is what you call the rating of the fuse. So the idea is if the current goes above 3 amps, this fuse will melt. Now here's why it happens. In the construction of a fuse, we have a glass cartridge, 2 metal caps, and here's a wire. Now this wire is designed to melt when the current goes above a certain value. So usually what we do is the rating of the fuse is slightly above the actual working current. Now in this example washing machine, we have working current is 4.5 amps. Let's say this is a 5 amp fuse, a bit above. So under normal conditions, no problem. Current will go through it and everything will work. Now let's say after some time, something happened, the washing machine got damaged. Now, when it gets damaged, now let's say the live wire accidentally now touches the metal casing. Now, this is dangerous. The next time a person touches it, the person will get an electric shock. Now, the prevention here is the earth wire. Here is the earth wire, the green and yellow striped one. So the earth wire is just connected to the metal casing. So under normal conditions, there'll be no current through it. However, when the live wire touches the metal case accidentally, what will happen is this becomes live. Now a large current will surge down to the earth. Now this is literally connected to the ground and then driven into the earth using a metal pole or a water pipe. So a large current will surge. It's not 4.5 anymore. It goes up 4.7, 4.9. But the moment it goes above 5 amps, the fuse melts. Now the circuit will not get any more current. Now, although I took a minute to explain it like that, in reality, what all you see is you go and turn the washing machine on. Within a fraction of a second, there's like a surge of current, and then it just doesn't work. Now, here's what you can write if they ask this in a 6-mark question in the exam. Please pause the video and take a minute to quickly read this through. Electrical power. The formula for electrical power is P is equal to IV. Now, some people use an Ivy leaf to memorize as in like IV. There are 2 other variations of this. So, we know V is equal to IR, and for this V, I can put IR. So, what do I get? I times IR, I squared R. Similarly, P is equal to IV, V is equal to IR, so I is V over R. And I can put V over R for I, then you get V over R times V, which is V squared over R. So here you can see all 3 variations of this formula. Here's a typical exam style question on this aspect. Please pause the video, give it a try. When you're ready for the answer, you can press play. And here's the answer. Now, the question is to calculate the power of the resistor. Now look, we have the voltage and resistance. So what is the formula with V and R? Obviously, it's this one here. So what do? We use P is equal to V squared over R, and it's 20 squared divided by 8, and you get 50 watts. Now, that's the first part. The second one, what's the amount of energy dissipated by this in 2 hours? Now remember, from the energy topic, power equals energy divided by time. So power is 50. I'm going to calculate the energy. Now remember, the time should be in seconds. So I know 1 hour is 60 minutes. 1 minute is 60 seconds. So 60 times 60, 1 hour is 3,600 seconds. Now 2 hours is 2 times 3,600 seconds, which is 7,200. And all you do is multiply those 2 together, and you get 360,000 joules as the answer. The national grid. The national grid is the network that connects the power stations to homes, factories, and other buildings using a system of cables and transformers all over the UK. Now, they have step-up transformers and step-down transformers. So, next to the power station, we have a step-up transformer, which increases the voltage to like a really high value, close to 400,000 volts or something. Then, near the consumers, there is a step-down transformer here, and that will reduce it to around 230 volts. Now, why do we use these high voltages for the electricity transmission? The reason is power is I squared R. Now you can see when you have a high current, there is a lot of power dissipation. So if you use a high current, a lot of heat energy will go into waste. Now to reduce it, because P is equal to IV, so if you increase the voltage, what will happen to the current? Because the power is constant, the current will go down. So we use large voltages and lower currents for the transmission, and we change it the last moment before we give it to the consumers. That's electricity done. Remember, lots of marks just come from remembering which formula to use and plugging them in the correct way. So keep those formulas super fresh in your brain. Here's a mini quiz on electricity. Pause the video and give it a try. Here are the answers.